Today is another hands-on sort of practical exercise session. So it's basically a continuation of last week's. So the slides are mostly the same as before, apart from something that I want to say at the end of this lecture. So last time we did this first exercise, which was a simple transformation of an array of structures to a structure of array. And some of you already sent in your plots, so I think a lot of you already managed to complete this. And today, so I will briefly just cover this again, just to refresh our memories of what we said last week, and then I will move on to the second exercise, where we apply sort of what we learned before in exercise 1 to a slightly more meaningful, let's say physically meaningful problem of a two-dimensional stencil operation, or a Laplacian. So, okay, that's just from last week, that you can, it's the same branch of the exercises, the same exercises branch of this EuroPLEx 2020 repository in GitHub. So I'm going fast because these are the slides that we covered last time, but just to remind you, so we had to transform the data layout of a kernel. Okay, yes. So this was the kernel that we were applying. So we had an array, which was an array of structures with X, Y, Z, and T elements. And then we wanted to fill in the S element by doing this operation. And we talked about how this operation is not very well amenable to vectorization because of the way that the data is laid out. So in the first task, you had to compute the number of floating point operations in I/O, and we covered that together. And then run this as a function of the vector length, and you got a plot, which was something like this. If you're using a similar laptop than me, I also did a plot on the right-hand side on an Intel Xeon system, which ended up giving me something like this. And we talked a bit about what this bump meant here. That it's basically, if you have this picture of the CPU, then basically when the array size is small, then all the data fits into caches, and so all you're doing is basically reading in and out of cache as you loop over and take the timings of this operation. Whereas when you increase the length, then the arrays start not fitting into cache anymore, and so every time you iterate and every time you take a timing of this comp S kernel, then you need to read and write from this green area, which is the main memory. And so this here, this performance that you gain here is more representative of what you would require in an actual application. Okay, and then we talked about how to transform this data so that you have, basically you go from an array which is an array which has member elements which are scalar to a shorter array which has member elements which are themselves arrays, something like this. And your task was to basically complete the kernel in case that you have arrays like that. And okay, let me move into the screen. The solution of this, although I think we covered this mostly last time, but it'll be something like this, where basically first you loop over the outer index and then the inner index, and you do the same operation. So you're doing the same operations as before, but you get, well, in this case, you get some slightly higher performance when you're in cache, but almost the same performance when you're out of cache. And then one thing that I did when I was making this program is up on top here, this vector length, this VL variable, which is what is the length of sort of the inner length of the arrays is variable. It's defined at compile time, but you can change it and run it again. And that's what the third task of this exercise did. So basically there was a loop where would you recompile the code for a different vector length, and then you would do the timing again. And in that case, most of you got a picture like this one, either the left one or the right one. I'll click next to go to a log scale. Yeah, so you get something like this. You can see that here at the more meaningful side of things, where L is large, as you increase the vector length, then your code becomes more optimal to use these vector registers. And so your performance improves. So it transitions to basically saturating the bandwidth, which is somewhere up here. And this can be something of a factor of 2, or in this case, a bit, remember this is a log scale, so this is a bit less than 2, but nevertheless significant improvement if you consider how small the change we made was. Okay. Does anybody have any questions here before I move on to the next exercise? Okay. So next, okay, this was a bit of a trivial problem, right? So next, I want to explain to you a bit how this applies to maybe a more meaningful physical problem that you might want to implement in code. And for that, the example that I have is consider something like a 2D stencil operation. So if you're researchers in Lattice QCD or in Lattice field theory, which I guess all of you are here for, then usually you need to invert sparse matrices applied to a vector, and the sparse matrix is typically represented as a stencil operation. So basically, it's an operation where you have an input vector, so you have a vector that this operation is applied to, and what it does is it couples some kind of nearest neighbors, like in this way. So in the case of like the simple Laplacian that I will use just to demonstrate the ideas here, right? In the case of the simple Laplacian, this would take two-dimensional Laplacian, right? So you apply it onto a vector of a two-dimensional vector which has an x and a y coordinate. Then to get the result, right, in this case phi, you need first of all the diagonal element, which is this psi of xy, and then you need the nearest neighbors, like x plus 1, x minus 1, y plus 1, y minus 1 here. Okay, and if you write this as a naive loop, then okay, b here is phi, and big A here is psi, then this is what this operation looks like. And if I unroll this just to look to see what it looks like when let's say four consecutive iterations of this loop look like, then you see something like this. So similar to the problem we had before, we see that the arrays that you need to do operations on, like this A array here, are not nicely aligned, so you can do the vector operations as we said before. So this AY comma X element is added with the AY comma X plus 1 element, which if you would load this into a vector memory, into a vector register, would be the next element in the vector, right? So this is suboptimal. So the compiler in this case, or whatever the runtime, would require doing a lot of shifting and shuffling and transposing the elements in these vector registers in order to get them nicely aligned to do this operation vectorized. And that would mean that your data layout in this case, as before, is not really laid out in a way that is friendly to, which is amenable to this vectorization. Okay. So one thing that you can do in order to facilitate this is to rethink a bit how you store these arrays. And this is very similar to what we did before. So basically you take the array, which is written like this in the original form. So you have a y and an x component, and x runs fastest and y runs slowest. So your x goes from 0 to L minus 1 and y goes to 0 to L minus 1. But you laid out so that part of this y-axis is actually running faster, right? So because these are distant elements, this will improve things, as we will see in the next slide. So if you have this y1 now going from 0 to 3, right? So in the case that you're doing it for 4 elements, and you have the y0 components going from 0 to a quarter of the extent of that dimension. And then this y maps to these 2 coordinates in this way. Okay, so how can we see that this works? So if you were to write this out, again, unroll the loop as I did in the previous example, but now in terms of these VAs rather than the A's, which I laid out differently, then you see that you have VA of 0, x here, right? And VA of y0, and the neighbor x plus 1 here, but this neighbor now is not the next element of the vector register as it was before, because the next element of this vector register is a faraway point that does not talk to any of the other elements, right? So basically what you took is the size that are needed to make the nearest neighbor sort of stencil here are all far away in memory, if we do it this way. And so you don't need to reshuffle the data that you read into a single vector. So as long as we start with the data structures ordered this way, right? So it would be pointless to have this data ordering and move in and out of this new convention and the old convention every time you call the kernel. The idea is to have your data, your fields, right? Your A's and B's, in this case, stored in this data layout, and then do this operation repeatedly, or how many times you need in some kind of solver, some kind of conjugate gradient. Okay, and a way to visualize this is how you had it in the previous data ordering, right? So you have some arbitrary point on the lattice here, y, x, and then the next element in memory is this y, x plus 1, and the next element in memory is this y, x plus 2, and the next one in memory is this y, x plus 3. And when you load now into a vector register, like the continuous data, then basically you're taking these 3 dots here, which are in one line, and you're putting them into a vector register like this. And then in the loop where you do the Laplacian, the problem is, and I repeat that, is that you have operations that involve this guy, but also this guy shifted by 1, and this guy shifted down by 1, and that's what causes the problem, right? Because you need the x neighbor, the y neighbor, and that's what makes it not very friendly to vectorization, right? But what we are going to do with this new data layout is basically we partition in some way the lattice into 4, and then what we do is we make it so that these elements here run faster in memory, the ones that I colored vertically. So those now go into a vector register in this way. So you have the first component being basically y, x, but on the first quarter of the lattice, the second component being y, x, but on the second quarter of the lattice, etc. And so when I want to do now the Laplacian operation of this, I need to combine this with its neighbor, but its neighbor are the 4 dots that are, x plus 1, which I'm showing here with my pointer. Okay. So you pack that into a vector register like this, and then all the operations become very easy to vectorize. Okay, so to summarize, reorder the data layout as I showed previously, and then your loops will become something like this. And then the stencil operation, you can sort of unroll in this way, and you see how all the operations nicely aligned. Okay, so one thing that I've hidden from you is what happens at the boundary. So what happens when you actually get a point, like somewhere around here, which is basically this point packed with that point, packed with that point, packed with that point, and you want to get the neighbor in Y. So that's when this does not follow through very nicely. So what I wrote here is fine, except for the cases where y0 equals 0 and y0 equals L over 4 minus 1. So these two edge cases, you have to do something special. And in order to see what you have to do, let's just look at the y equals 0 case. So for the y equals 0 case, what you need to do is something like this, right? So if you have periodic boundary conditions, then this is now with the original data layout, so not reordered, and you have something like this. So you have ax plus 1, ax minus 1, that's all fine. A of 1x, so that's the neighbor of y in 1, but then y minus 1 needs to be L minus 1, okay? So in the vectorized form, this is what it will look like. So everything looks the same, except for this last one, which is not ordered as everybody else, but is ordered shifted by 1. Okay. Now this you have to sort of take a moment and maybe write it down and think about it a bit more. I don't expect you to sort of immediately grasp this, but the point I want to make is that you only need to do shuffles in this new data layout format. You only need to do some shuffling of the data in the vector, in this 4 vector here, on the edges. So it's much rarer than what you would do if you had the original layout, which you need to do it for every iteration. Okay, for the other boundary, then the shift is in the other direction. So here you need to go from sort of the 0, 1, 2, 3 layout, you go from 3, 0, 1, 2, but for the other boundary, you need to change this element, and this has to be shifted up by 1. Okay, so that's the main idea. And to demonstrate this, I've prepared another exercise. It's a bit more involved than the previous simple one we saw, and also it's a bit. I made it a bit more meaningful for like lattice gauge theory. So, as I said, this is to demonstrate the concept here of sort of reordering the data layout of the fields, and for that I've create an exercise which uses not the naive Laplacian, but the so-called gauge Laplacian. So basically it's a 2-dimensional Laplacian, which again, you have a diagonal term, which is 4 times the midpoint minus, and then the sum of the nearest neighbors. But every time you hop by a nearest neighbor, you need to multiply by a U1 field, right? So that's why it's gauged. So there's like a gauge field at every side pointing to the 2 directions, right? And every time you hop, so every time you take a neighbor, you need to multiply by this U1 field. So there's 2 data types here, right? It's like a lattice QCD or the Schwinger model, or but it's 2-dimensional. So at every point there's a fermion field that sits on the sides, which is just a scalar complex number. So it's not really a fermion, but in any case, just for the purposes of this exercise. But there's also two U1 links, one that corresponds to the link pointing to the 0 direction, and one corresponds to the Y direction, okay? So in the code, one of these fields, one of these 5 fields is initialized, or psi fields. A gauge field is initialized, so the U's are initialized. And then what is done is a CG is applied to these fields, so a conjugate graded solver, right? So an iterative solver is what it looks like. So if I represent this Laplacian operation with a D, so D on X is the same as what I showed before. So D applied to that is basically this operation. So the program basically initializes a D, initializes some gauge fields U, which are hidden in this D, and then computes X as the inverse of D on B by carrying out this CG. And you can see operations like dot products here, etc. A alpha times P plus X. These are all implemented in these linear algebra functions. Okay. And when you run the CG, so you run it like this, /lap. So this is in this lap folder of the exercises, and you give it a length. So the actual length of the array will be 100, in this case will be 128 by 128. And you will see the iterations going, okay? And then it will converge, and your version will not report the time because that's something that you need to fix, okay? So as I said, this is in directory lab, and there are some to-dos in this. So by the way, for this first exercise, we use a naive data layout, okay? So basically you have complex fields that are real and imaginary parts separately. So these represent what I'll call fermions in this case, this scalar thing, which is not really a fermion. And then this is the number of dimensions, which is 2 in this case. So these are the sort of the gauge fields. And so there are structures of these type, right? So L times L of this is allocated, and L times L elements of this structure is allocated. And those are the matter fields and the gauge fields. And then, as I said, a conjugate gradient is carried out, but there are some parts missing, okay? So there are basically only 2 parts missing. Which I will show you where's my Emacs buffer? Here it is. Let me navigate to the code. Right. Okay. So you don't need to worry about most of the code, but of course you will want to take a look. So some of the functions are the same that were in the other program, like timing functions, etc. I'm going to jump down to where the CG is done, just to show you don't need to do anything in terms of the CG, but here you can see fields being allocated, the Laplacian being applied, some linear algebra operations required, and then this is the main loop of the CG, okay, where basically you have one application of the Laplacian in each iteration, okay? And this is timed. So every time you call the Laplacian, this is timed and accumulated, and in the end, we want to report how many floating point operations per second we achieved and how many bytes of I/O we achieved. So your tasks here are 2. First, to count the number of floating point operations and the number of bytes of I/O that need to be read in and out of memory in order to complete this Laplacian. And then you also need to complete the main hopping part of the Laplacian, okay? So this is where this Laplacian is applied. You pass the size of the box, and the input array and the output array and the gauge field. And I do some index arithmetic here. So basically V00 is the midpoint. So it's X comma Y. V plus 0 is the plus neighbor in Y. So it's X comma Y plus 1. And so this actually imposes periodic boundary conditions with these modular operations here. So what you need to do is compute the real part and the imaginary part of this operation here. So you need to multiply with the right index of the gauge field times the right part of the fermion field for the real part in the direction x plus, the imaginary part in the direction x plus, etc. And if you get it right, then you should see exactly these iterations when you use 128 elements in the up diagram. Okay. Okay, so oops, sorry. Yes, and then when you get it right and you compile this, you should be able to run the script, which will basically again run the Laplacian now, run this operation, but for varying length. And then again, as in the last time, you can plot using Python, using this Python script, and you will get a plot which shows if you get the number of floating point operations correctly in the calculation, you should see the floating point operations as a function of L. And this is again on my laptop here and on another system, a cluster system. Okay. So, oops, going the wrong way. So, yes, I think I'll give you, why don't we take about half an hour for you to take a look at the code and maybe try a few things, or maybe ask me some questions about if you have any questions or clarifications, and then I show you how one would solve this, and we run it together and see the results. So that's up until 4:45. Sorry, your time zone. Well, in 30 minutes. So for you, it would be 4:45, I guess. Yeah. For most of you, at least. And please ask questions if you have questions. So this 2 times nd here is basically this diagonal part. So I already filled in. So this is 2, nd is the number of dimensions, which is 2. So 2 times nd here. This variable is defined up here. It's 4. So this 4 times the input array, 4 times psi, is already done here. And then I'm subtracting this part, right? So P real should be the real part of this, and Pm should be the imaginary part of this guy. And then I've just broken down the terms here that you need. I mean, it doesn't have to be in this order, of course, but I just wrote them in a specific order. And so remember that this V plus 0 is, so V00 is basically just the X comma Y without any neighbors. And then the other 4 address the the nearest neighbors that you need to take. So in each line here, you will need to do basically a multiplication of a gauge field with some index with one of these fields with some index. But remember that these are complex, so you have to explicitly write out the real part, the imaginary part. Somebody want to try and give me this first line here? Maybe you need more time. So in analogy to what was just okay. So in this simple case, right, you have this simple Laplacian. Okay, so I could if you were to, so this problem is the same as the one that you're working on now. It's just that you don't have gauge fields multiplying these fields, right? So you don't have any u's. So if I go here to this equation, yeah. So if I just remove the u's here, if all the u's are 1, then it's exactly the same as the other Laplacian, right? So it would just be 4 psi minus paren, and then you would have psi in plus x, psi in minus x, etc. And in that case, okay, psi in this case is, you know, this input vector, right? And it's got a real part and an imaginary part, but let's just, for the sake of argument, assume, let's just forget about this dot phi. So basically you would need to do so you'd need to add with v minus 0. Okay, so that's, so this is the index, this is the element of this array in the plus y direction. This is the index of the array in the minus y direction. And now we will add, well, yeah, the neighbors in the x. Okay. And the neighbor in the y. So these would be the 4, like this one would be, this one would correspond to plus in y. So these would be the 4 terms that are missing in this case, okay. Now it's a bit more complicated. First of all, these are complex, so they have a real part and an imaginary part that you need to address. Okay, so if you don't have any gauge fields, then of course, then you just add the real parts and you add the imaginary parts. But now you have gauge fields to multiply with, which are themselves complex. So you have a field that you have to put here in front, so you have to multiply this with g of something. Sorry. So all the terms here need to be multiplied. Something like this. Yeah, and you need to know what to put here, right? So in this, so the gauge field at xy, you can tell by its structure, right? So at each element, at each lattice site, there are 2 elements of the gauge field, and you can consider that the 0th element, it says it here. So the 0th element is the one that points to the the 0th element is the one that points in the y direction, and the x element is the one that points in the x direction. Are you still with me? Or have I lost it? Yeah, it should be. And the x and the sorry. Okay, let me say that again. So you have an array of L square of these. And the 0th index here is the one that points in the y direction, so that case there. And the one with the indexed here is 1 will point in the x direction there. So when you're hopping back to here, back to this to-do, okay. So when you're hopping in the x direction, you should use, you do something like this. Okay. Let's do it together. Okay. So we need to take the neighbor in plus x, right? In that case, right? The neighbor in plus x of psi, and the gauge field in the x direction of x comma y. So times the gauge field, right? It's G. What did I name it? G. Yes. So this is V0, 0. And then this would be U of 1, right? Because it's in X. Okay. But now I've hidden that this is complex and complex, right? So it's the real part. So I need to address the real part. So the real part is the real part with the real part minus the minus part with the minus part. The imaginary part with the imaginary. Okay. So that's the real part in the plus x direction. Okay. I'll just copy paste this, or maybe not. So the imaginary part, so, you know, so again, the real part, I have to multiply two complex numbers. So the real part is real times real minus imaginary times imaginary. So the imaginary part is just now the cross terms, right? So it's the imaginary part of that. Times the real part of that. Sorry, plus. And then the other way around. So the real part of that guy and the imaginary part of that guy. Okay, so now these two basically correspond to, if I just go back to the Laplacian, which might be easier, basically correspond to this term. X plus 1 comma y. It's just that, again, now it's complex and it's multiplied by a gauge field. Okay, the backwards one are a bit more tricky now because remember, right, so you need to go, for the fermion term, it's easy because it's just, instead of V0p, you will take V0m. So it's just the neighbor in the minus direction. Okay. But the gauge field is, you have to go, you need to take the gauge field that points in the backwards direction, which is basically the conjugate of the backwards pointing one. So you need to hop back and take the conjugate. It's written here. Okay. So we will take the backwards neighbor of like this. And because the gauge field is conjugated, then this will flip the sign of the, when I use the imaginary part of the gauge field, this will flip the sign. So sorry, it's real. So again, the imaginary part is the cross terms here, but of course, the fact that the U field is conjugated just flips the signs. Okay, and then exactly the same way you would do.
Sorry, Giannis. The second part of the third term, so the real part, direction x minus, for the
Yes.
fields, the structure of phi. The second term.
This one?
Yes, the second one you wrote dot phi I. Un.
I made it, yeah. So this should be phi im.
Okay.
And then this should be, yeah, okay, something went wrong here. So this is minus an x, yeah. Thanks. Okay, this will be the same, so I'll just copy that. It's just that now I need to hop in y, right? And hopping in y, I did is basically instead of taking 0p, which is v0p, which is x plus 1, take vp0, which is related to y plus 1. Just transpose that. And of course, the gauge fields now are pointing in the 0 direction. Okay. Admittedly, this is a bit fast that we're doing this, but hopefully you can get something out of this and then study it a bit better sort of offline. And of course, you're free to ask any questions or email me about this at any point, even after the school has ended. Okay, and now that's the y direction. Okay, so that's the one part we need to do. The other part we need to do is to count the floating point operations. And so all the complex arithmetic is laid out for us now. So all we need to do here is just count the floating point operations. So yeah, so why don't we go ahead? So here you have 2, 4, 6. And so there are 12, there are 24 of these operations. Right? 2, 4, 6. And there are 4 of these, so 24. But then we also have these additions. So it's 24, 26, 28, 30. So 30, and then another 2 here. These are 32 floating point operations. Let me just check something. So again, 2, 4, 6. So 24 here. +24 plus 6 is 30. Sorry, it's 34. So it's another 4 here. So 34 floating point operations. Right. So here we would put 34, but that's per lattice site. Sorry, it's already, so down here it's multiplied by L times L. So 34 operations. Okay, the other thing is how many bytes of I/O? Well, every field here, every number, so at every lattice site, we have one of these psi fields, which is a complex, so 2 floating point numbers. And then for the gauge fields at every lattice site, we have one pointing on to the right and one pointing upwards, so we have 2 gauge fields. So I'll just put size of float because everything is float. So every time we apply the Laplacian, we need to read once the input gauge field. We need to read once the, well, spinners, let's call them, the fermion fields, and we need to write once the fermions. So in that case, okay, so the fermions 2, because they're complex, the gauge fields are 2.
Sorry, how is it with the fermion fields for the I/O?
Excuse me, how is
it for the fermion fields?
So at each lattice site, you have a complex number, right?
Yes.
And the complex is 2 floats.
Mm-hmm.
And you need to read one in, and you need to write one out.
Oh, this is per lattice site.
Yes.
Okay.
And then the gauge fields at each site, you have one pointing up and one pointing to the X and one pointing to the Y, sorry. So you have 2 of those, and again, they're floating point numbers, and there's 2 per site.
Okay.
Okay, so let's see how many typos I made by trying to compile this. So that would be make A. Of course, I made a mistake. This should be an IO. And then if I run it, right, so I get some number of iterations here. It should converge 4, and if I did it correctly, then one thing you can check is check that the last iteration, so if you got it correctly, then the way I'm using, I check this also on different systems. So I'm seeding the random number generator with the seed of 7. So because for all of you the seed is the same, this should create exactly the same random fields, and so you should see exactly the same number of iterations and last iteration. And I can confirm that at least in my case here, the code that I completed on screen while you were watching does indeed produce the same last iteration. And so this gets about something like 2.5 gigaflops per second. So by the way, after the course, I will put the solutions up. But okay, so, and if you scan the number of the length, then you get something like this. So this is something that I would just urge you to play around with it once we're offline and you have some more time to think about it. But anyway, but the thing is that what I've done is I've also prepared a version of this which has the same structures, the gauge fields and the fields, but they have this new data layout, right, where they have a vector length running fastest. Now, we won't do it here during this course because that would take too long until we get accustomed to everything and, you know, all the different structures. But basically, it's the same code, right? But now it's written in terms of these new structures. And again, there are some pieces missing that if you want and if you're interested, you can try and fill them in. But the pieces that are missing are, well, again, the number of floating point operations. So this is Laplacian v.c. So make it a bit larger, sorry. Okay, so the to-dos here. So this part, you should just copy from the solution that we just did together, right? Because it's the same number of floating point operations and the same number of bytes of I/O. So that's a bit trivial, but the main part that you need to do, and okay, this is very complicated. I mean, this is very not complicated, but needs some time to digest, let's say. So that's something. That's why I'll let you do it sort of offline. But basically, all these structures are copied into temporary vectors because on the boundaries we need to do some shifts. And then, of course, this part is also left for you to complete in the same way we did it for the original data layout. Now, when you put everything together and you run it, you should get exactly the same. This is a way to check, right? You should get exactly the same history of the iterations of the CG. So the residuals should be exactly the same from the first iteration to the last one. It should converge in exactly the same number of iterations. So that's for you to check this more, let's say, error-prone vectorized version to the original version. And then what you can do if if you run the script, then you get something like, okay, so on my laptop, it was something like 1.5 times faster. And on this cluster machine, it was something like more than 2 times faster when I use this vectorized version, which is a blue point. And as in the case of the other problem that we saw last week, there is a script that would basically loop over the vector length, right? So it's changing the vector length and then it's running it and it's timing it. And if you do that, then you can see what the optimal vector length is for the machine you're running on. So for example, here on my laptop, the optimal vector length was this green one, which is 16, whereas on the cluster that I run, it was 32. Just because the architecture is slightly more different, or maybe the number of operations that can be issued in a single cycle is different, and that changes what the optimal vector length is. But what is noticeable here is that you, from going to from the naive implementation, right, to this new data layout, you can get some very impressive speed ups. And again, you're doing exactly the same number of operations, you're getting exactly the same results. So we haven't fiddled a bit at all with the number of operations that are being done or anything. It's just, we're just changing the way that we access the data. And okay, I mean, I guess the important take-home message, if you like, of this is that you should keep in mind that this does play such an important role depending on the architecture you're on. And so if at any point or when you need to start writing, I don't know, a new code for a new architecture or something, let's say, that implements some of these stencil-like operations, right, which is very common in our field, then it's good to keep in mind from the beginning that your code might need to be flexible to change these data layouts, or do it just from the beginning, okay? Because then it will save you a lot of optimization work in the future. A lot of the codes already, a lot of the available codes like Grid, I mean, some of you are working in collaborations probably that use Grid, or other codes, similar codes already have this in some form built into the data structures. And so I think it's also useful for you to know a bit what's going on when you see data structures which have, you know, indices running faster, which might not look reasonable to be running faster. Okay, so yeah, please feel free to try this at home, and ask me even after tomorrow's lesson is fine if you want to understand this a bit better and have some questions. I will probably during the weekend I'll try and put the solutions up in a branch of the repository. Okay, so I have a few slides which is not an exercise remaining that I want to discuss with you a bit. But before I go there, do you have any questions regarding this part? Regarding the exercises? No. Okay. So yeah, so having talked about that, in the next probably won't take the full time, I want to talk a bit about some practical considerations when actually implementing a bit more fully fledged, you know, software like the ones that we've seen today. So for the purposes of this exercise, let's say, I'm going to walk you through computing the computational intensity for the case of the Schwinger model. So we saw how we did the exercise, the practical exercise before, about counting the number of floating point operations that need to be carried out in the case of that sort of gauged Laplacian. But we didn't do any considerations on, you know, how to do the same thing with less floating point operations, etc. And when you actually go into like real gauge theories like this one, then there are some considerations you can make that can actually make a difference. So for the purposes of this, we will look at a specific operation, which is this, you know, Wilson sort of fermion action for the case of the two-dimensional Schwinger model. So basically you have U1 gauge fields like we had in the previous exercise. You have two dimensions like in the previous exercise, but now you have fermions. So these psi's now are two-component fermion spins, okay? And you can write the application of this operator on a vector like this. And it's similar to sort of the gauge Laplacian we saw before, except that you also have some multiplication with 1 minus sigma mu here, or 1 plus sigma mu here, where these are the Powdery matrices, okay? So here I've written explicitly out the components Okay, so this is 2 by 2, 1 minus sigma mu is a 2 by 2 matrix. U mu, this mu is just showing the direction, it goes 0 and 1. And beta then is this two component fermion field, which multiplies this 1 minus sigma mu, right? So that's just the hopping term here. And then you also have the mass term, m plus 2, in this case, times the diagonal element. So, okay, so we learned how to count the floating point operations when you do like complex multiplication. So one could just naively come here and do this. But that's where the point of this exercise come in, is that there's actually a lot less floating point operations that you do need to do in order to do this operation than meets the eye by just simply looking at this operation here. So let's start unpacking it. First of all, one thing that we need to keep in mind is that this fermion matrix is so-called sigma Z Hermitian. In QCD, in lattice QCD, a lot of the operators are gamma 5 Hermitian. So this is the correspondence here, which means that m by itself is not Hermitian. So m is not equal to m dagger, but sigma Z times m is equal to m dagger sigma Z, right? So if you apply the third Pauli matrix from the left to the matrix it's equal, then that is basically Hermitian. And what that really means is, you know, I just wrote this here explicitly with the indices written out. So that means that in a conjugate gradient where we need, for example, a Hermitian matrix, where we usually need to apply m dagger m on a vector like m dagger m psi. In this case, we can get away, we don't really need to implement m dagger, right? We can just implement m, and then m dagger m is just sigma z m, okay? So in solvers which need a Hermitian matrix, we can get away by only implementing the forward application of m on a vector, on a fermion. So that's one thing. Okay, and the other thing that's important is that if we write out what this, so remember, I'll go back a bit now. So remember, we have, here we have 1 minus sigma mu and 1 plus sigma mu, and mu goes from 0 to 1. So we have 1 minus sigma x, 1 plus sigma x, 1 minus sigma y, 1 plus sigma y. So another thing that comes up is that if you write this out, right? So you take these two component vectors and write them out like this, then you notice that the two components are basically, in this case, they're the same. They just change by a sign depending on if you add sigma 0. And in this case, they're the same. Just the one is the imaginary part of the other. Okay. So this means that, so first of all, a multiplication by I, right, is not really a floating point operation, because all you're doing is exchanging the real part with the imaginary part. And it's also a sign flip. So that's 0 floating point operations. So that means that in order to apply these matrices 1 plus minus sigma 0 and 1 plus minus sigma 1, you only need the addition or subtraction of two spinors, right? Of the 0 component and the first component. So it's either psi 0 plus psi 1 or psi 0 minus psi 1, and then you just need to appropriately change real and imaginary part depending on if you have i's in there. So basically each one of these operations is just 2 floating point operations, right? It's a spinor addition, or it's a complex addition or subtraction. What's more is, you remember that when you actually do this operation, then you need to multiply. So here you need to multiply both components with the gauge field in principle, right? But of course, the gauge field commutes with the projection with minus sigma mu. So really, since you know that the values are related in the top part of the projected spinner, like in this case, in the bottom part, that means that you only need to multiply only one component with the gauge field, right? So that saves you another factor of 2 in floating point operations. So if I were to write this out again, and I'm talking now about the hopping term, then now you see that there are 2 terms, right, in each direction. So in the 0 direction, you have this 1 minus sigma mu term and 1 plus sigma mu term, and then you have mu 0, 1, so you have 4 terms. And in each term, you need the multiplication with this Powdery matrix, which we said is just 2 flops, right? It's either an addition or a subtraction. And then a multiplication by the gauge link, which is just 1 complex multiplication, which we saw last time is really just 6 floating point operations, right? It's 3 for the real part and 3 for the imaginary part. And then just adding all these terms together is just 3 complex additions, so another 6 floating point operations. So for the hopping term itself, this is just 38 floating point operations. And then the mass term, which I don't have here, which is just this plus, you know, m plus 2 times the spinner, is just another 4 floating point operations. And then adding the mass term and multiplying the hopping term by half is another 8. So that's a total of 50 floating point operations per lattice site. Whereas if you were to just calculate this naively, right, you would have gotten something like 4 times this, right? So if you implement this, just looking at, you know, just doing explicitly the multiplications and the matrix multiplication, then you would find something larger than 100. So coming back to the computational intensity, the application is 50 flops per site, right? And then if you look at the data I/O, assuming that you have double precision, in this case, structures, then you will get an intensity of about 0.52, right? Which is to say that on usual high performance system, this is severely bandwidth bound, right? So you're always, so the intensity of modern systems is much larger than 1. So our kernel intensity is much smaller than the machine intensity. And so this means that this kernel is bandwidth bound. Okay, and then for the Hermitian, so for the Hermitian operator, so for the case of sigma z m sigma z, remember the multiplication by sigma z is just a sign flip of the second component, right? So sigma z is 1, 0, 0, minus 1. So multiplication by sigma z does not take any operations. And so the intensity of this operation is the same as just one operation, right? It will just be the same if you assume that all fields that need to be read and written in each application. But of course, if you assume that the gauge field stays in cache, then you can achieve a bit higher efficiency. So, then you will get an intensity which is a bit higher than before. And so you might be able to get better performance if you are on a machine and if you have ways to keep the gauge fields not to be loaded every time you apply M. The psi's probably you need to load them every time, because usually in a CG it's the right hand side that changes all the time and you need to apply again and again. Okay, so that's it for what I had wanted to say for today. So for the remaining of the time, you can work on you can work on maybe trying the first exercise. Well, first of all, do you have any questions on this last part about the computational intensity with the Schwinger model? No? Okay. So if you don't have any questions there, then what we can do is you can, work on the first part of this Laplacian exercise. The part that I did. Let me come back to the solution. Part that I did here. So you can work on this, filling in, where is it? Yeah, filling this in and then compiling it and running it and letting me know what kind of performance you get or if you have any issues there. So I can stay on until, past. Okay. So I'd be interested to see basically what kind of performance you get on your systems. So it seems that even for my laptop and on this other machine that I used, which is a cluster node, the performance was around 5 gigaflops. That's probably a coincidence, but please try this out and let me know what you get. By the way, tomorrow will be regular, won't be practical. It will be a lecture, okay, for the last lecture, which is tomorrow morning.
Hi.
Mm-hmm.
Could you show the code once more?
Oh, sorry, I hit it.
Mine is not converging yet. Yeah, let me check.
Anybody who might want to ask something about last week's exercise can also ask, of course.
I think I got something similar to your plot, but maybe it's because the same laptop. It's an i5.
Yeah.
So
You got around 5 or so gigaflops,
yeah, it's like
and relatively constant with the length.
6, I think, and almost
Yeah.
constant.
And you check that your iterations, your residual, that this is correct, right?
Yeah, that's the problem. Mine is not converging. I just checked the code and it seems the same, but I'm not sure. I think it's the same, but just by eye, I can't be sure.
You want to share it privately in the chat, so
I can
free to do that.
I can just copy and paste. I don't know. Maybe I just sent it to you, but maybe it's not helpful like this. I'm not sure.
Let's see. Did you try it, Nelson?
Yeah, it worked now. Thanks. I'm gonna see the plot to see if there is any difference.
Sorry, Giannis. Instead, for the to-do B, may I ask you something for the very first one?
The
For example,
very first?
the real part in direction x plus. I would write it.
Yes.
Yes, but for the other one, when we vectorize with
Yeah.
the structures.
Yes. Do you want me to open that?
Yes, if that is possible. I mean, I just want a confirmation.
Sure. Yes, fine.
Yeah. So for example, the very first one would be in underscore v0p underscore re times g v001 re, right? Something like.
Yeah, so that would, yeah, so basically,
But,
just copy this one. It'll be, well, maybe I don't even need to. I mean, it'll basically be this line, right? I'm taking this from the non-vectorized version. Okay, Lorenzo?
yes.
And I need to put a J here.
And actually you can remove the brackets in v0p and put underscore. Because you define these structures above.
Oh, sorry, yes, I forgot about this. Yes. Apologies, I forgot what I did. Yes, you're right. So, yeah, yes, exactly. That's the whole point. Yeah. Sorry.
Okay.
Like
And,
this, right?
And a J also in after v0p, right? Okay, yeah. Okay. And also G, also the links should be without the brackets, right?
Yes, also the links, yes. So the trick is, so that will be this, yeah, exactly. So I think you got it here. So this will be, do I have a one or do I have the one in the thing? Yeah. Okay, what is it exactly? It's G, VM0, 0. So it's G, yeah, this will be this will be 1, right? Like
Yes.
this, yes. So I have devised a naming convention for these, which is similar, and that's J. So basically, yes. So if you just translate this, it should just be the same. Just
Yes.
with this new naming convention, it will be the same, and then the complexity is hidden somehow in shifting appropriately the neighbors.
Yeah, I see.
The tricky part is in doing that special thing for the neighbors, which to figure that out, one has to put on paper a bit. Let's see.
Understand. Maybe another question. Usually, when doing the smearing, people talk about we should be careful on the boundaries. Is due to this reason or? But
I think no. I think that's more physics. So, well, I don't know. So what? When you smear you mean you smear the right hand side, right? You smear the sources, we say.
yes, or also
When you smear, yeah, I don't know what that's referred to. Maybe it means, if you smear too much and you reach the edges, then basically you know you will you will get a field that basically never goes to zero.
okay, but I was referring to the problem is specific for the covariance shift, though, so that's why I thought that would be related to this vectorization.
I don't know. I mean, usually, no, because usually this, I would be surprised if that's the case, because these smearing routines are usually sort of the right boundary conditions are sort of built in, and that's not something you should worry about when you just call it from a higher level. But I don't know. If you give me a specific example, maybe I can elaborate on it.
But I mean, you already answered somehow. Thanks.
Leonardo, I have a question.
Yeah, hi. I think I just probably fixed it. I'm not sure because I did
Okay.
find a typo. But that just meant that it was not converging right.
Yes.
Okay.
Yes, I mean, if there's a typo or a mistake in which neighbors are coupled, then of course the operator might not be Hermitian anymore, right? Which means that CG is not guaranteed to converge.
Okay.
And what does it? It must have some. Yeah, max iter is 100, so it'll stop at 100 so that it just doesn't go forever.
But still, if I may ask, the plot I'm getting for the first part is seems to be increasing, not much, but still it's a kind of a small trend. Is that possible? Or
it's increasing with increasing L.
Yes, a bit steeper than what you had, I think.
I don't know. This is consistent, so if you run it several times, you see the same. The only thing I might, maybe on some laptops, okay, here's something. So some laptops, you know, they might be throttling. So you might actually need to, because the smaller sizes come first in the iterations, right? So first you'll run the smaller sizes and then it increases it. And maybe some power efficiency on the laptop will not spin the, will not spin the CPU fast enough until you reach these larger lengths. But this is just guessing now. I'm not 100%.
But do we also expect the same value of beta? Was it beta FP as the one? What is it? Around 5 or not really?
Oh, as in my slide?
Yeah. For example, or is this?
I think I just put some random stuff here because I hadn't. So I didn't want to give away the solution, right? Because if you were sneaky, you could have gotten the timing here and figured out what the. so these are just random. Don't pay attention to these numbers. You see what I'm saying?
No, I mean the slide with your plot. Sorry, maybe.
In the plot, yeah.
I have too many things open right now. Yes,
this one?
the beta FP, yes. Is this expected to be changing? I wouldn't say so too strongly, right?
As a function of L.
No, the absolute value, what does that depend on? That it's 5 and not something else?
On the laptop.
Oh, on what system you're running?
Okay, but I mean, does it depend strongly even if I have a laptop which is comparable to that one, or not really?
Yeah, it might if you have like higher bandwidth to RAM. Maybe you have maybe your laptop has more RAM, which means it has more channels. The CPU has more channels to the RAM, maybe, if it's a more modern laptop, and so you can read the data faster in, and so you might get a high performance there.
Indeed,
Sorry,
just to mention, I have the same kind of laptop, 4 cores, Intel Core i5, but with 16 gigabytes of RAM, and I get around 10 of this beta on my MacBook.
Yeah, I mean, it probably has more. Yeah, I mean, the reason I mentioned the size of the RAM is not because it's not because the amount of RAM matters per se, but because sometimes when you have more RAM, then this also increases the bandwidth. That's not always true, of course, but there are all sorts of factors. Or maybe the clock speed of your processor might be larger, might be 2.6, for example, instead of 2.3, which means it's a bit faster. Yeah. Yeah, others are also reporting that for smaller sizes they get, well, no, I think this is the opposite, that for smaller sizes they get lower performance than for bigger sizes. Oh no, this is the same that was mentioned before. Smaller sizes got lower performance than for bigger sizes. Yeah, I mean, okay, this is a bit hardware dependent. What's really interesting to see is how much this vectorization, so this folding, this vectorization helps, I think. Because the absolute performance is just a matter of your computer, but the improvement is usually something that will carry through to different system. Okay, we're about 5 minutes over, right? Which is okay, but at some point.
Sorry, just last thing. You said that the vectorization then depends on how you write the structures and so on. But you show in your picture, in your plots, that for two different systems, you can have very different results, right?
Yeah, so yes, so here, for example, I mean, in both cases it helps, right? It's just that the optimal is not the same. So, for example, on my laptop, when I went from 16 to 32, it reduced, right, and then went up a bit. Yeah, that just tells you that you have to keep in mind that the optimal vector length for a given machine is not necessarily, I mean, the same. It's something that's tunable. And it might even, in this case, it might depend a bit on the problem size also. But I think it does make a point here that on two different machines, it actually does help to, to a larger or smaller extent if you do the spectralization. Sorry, I mean, this is the one you were referring to, right? This plot.
Yes, or either the one before, but yeah, the same.
Yeah, I mean, 64 here is weird, right? So if you think about what's going on, you have an extent of 128. I mean, this is, okay, it's scanning, so it's not always 128. But for the case where it is 128, basically you only have two outer lattice sites and then 128 inner lattice sites. So actually, if you look at the operations that are being done, basically all the outer parts are boundaries. So it has to shuffle in every iteration in that case, right? It has to do this shift in every iteration in that case, because every iteration has a boundary of y. So when you use 128 here, we're not really expecting things to be much better. And indeed, this starts becoming a problem on modern systems which have very large vector registers. If you want to run a smaller lattice, then sometimes it becomes suboptimal, right?